Hello everyone. So in this video we are going to study Zener diode. Okay, but before that let's just revise our device physics. Okay, so in diode physics what we have studied, in forward bias we have a characteristics like this, right? Initially there is no current and then there is exponential current, and in reverse bias I said that there is a reverse saturation current, but at some point at the breakdown voltage there is a high current flowing. This is what I said, right? So now I will explain the reason why this is the high current is flowing. Okay, and from there we will get to our topic, that is Zener diode. Okay, so these there are two kind of breakdown. Here you are having breakdown voltage, no? So there are two kind of breakdown: avalanche breakdown and Zener breakdown. First we will study about avalanche breakdown. So now this is my PN junction diode. My diode is in reverse bias. Okay, it's in reverse bias. So I am, and there is this E internal field, right? Internal electric field is there. This we have studied already. Okay, so now what I am doing, I am increasing my reverse bias. What will happen? I am increasing my E external here, right? So this electric field will get increased. This total electric field will get increased, right? Now what will happen? They will attract these electrons. Although here also they were attracting those electrons, and there was, because of those attraction of electrons, there was this small saturation current was there, right? But now there is this strong electric field, so now they will strongly attract these electrons, right? There are these minority electrons are there, and the electric field is in this direction. So electron will feel the force in this direction, right? So electron will be forced in the opposite direction of the electric field. So now this electric field will strongly attract those electrons, right? Now they will strongly attract those electrons, and also these holes will be strongly attracted, or in this direction only. Sorry, in this direction. Holes will be attracted in this direction, and electrons will be attracted in this direction. So now these electrons will get high kinetic energy. Electrons are getting strongly attracted. That means they are feeling more force. More force, that means they are traveling very fast. Traveling very fast means they are having more kinetic energy. And now because of this more kinetic energy, these electrons will start colliding with these silicon atoms. They will collide with these silicon atoms. Now what will happen if they collide with this silicon atom? Let's just assume you are having an electron here. That is this electron. Okay. Now this electron goes and collide with this silicon. What will happen? It will knock out this electron and create a hole. It has knocked out this electron and created a hole. So this electron has been knocked out. So this was your free electron. This was your minority charge carrier, right? Minority charge carrier. Minority charge carrier. This was your bounded electron, right? This was your bounded electron, bounded from silicon. This was your bounded electron. Now, since this electron has knocked out this bounded electron, this electron has become free electron again. And there is this vacancy, that is hole. So now from one electron you are getting two free electrons. Now these two free electrons will go and they will knock out two more electrons, right? They can knock out any electrons. So they will knock out two more electrons. So what will happen? Here there will be vacancy created and we will get one free electron, right? What will happen here? We will have a vacancy, that means we will have an electron here and we will have a free electron. So now we are having 1, 2, 3, 4 free electrons. Now these 4 free electrons will knock out 4 more bounded electrons. So they will knock out 4 more bounded electrons. Now in this way what is happening? In this way we are creating a lot of holes, a lot of vacancies, right? In this way we are creating a lot of vacancies, and thus we are generating a lot of electrons. So from 1 electrons we are generating 8 electrons now, and similarly these 8 electrons will generate 16 electrons. So there will be a lot of electrons, and because of these much of electron there will be large amount of current flowing, and that is this current. That is this current. What happened in avalanche breakdown? Let's just revise it. What happened? There was already some internal electric field. Okay. Now I increased my reverse bias. So the internal field plus external field. So there was a lot of electric field, and because of this lot of electric field, electrons felt more force. Because of this more force, they gained more kinetic energy, and because of this more kinetic energy, they knocked out the bounded electron of a silicon atom, and one electron knocked out one bounded electron. So two free electron was there. Two free electron knocked out two more electrons. So four free electrons, and these four 8. So in this way, there were a lot of free electrons and there was a lot of current. So this was the region at all this happened at a particular reverse bias voltage, that was breakdown voltage. All this happened at breakdown voltage. So at breakdown voltage, there was a huge amount of current flowing. So this is what is happening. Okay, so this is known as avalanche breakdown. Okay, so I have written the definition. High energy charged particle knocks out the bounded electron from silicon atom, and thus creating electron hole pairs, thus creating large number of electron hole pairs, and the current increases. This phenomena is known as avalanche breakdown. Okay, and now what will happen if there is no limiting resistance? Okay, if there is no limiting resistance, that means this is a simple circuit. That means you are having a diode, and this is a circuit. Now the diode is working in breakdown region. So what will happen? A very large amount of current will flow, and this diode cannot take this much amount of current. Very large amount of current, that means there will be a lot of power. A lot of power means there will be a lot of heat, and because of this heat, this device may burn out. Okay, and no limiting resistance. What do I mean by limiting resistance? If there is some limiting resistance, so this resistance can take up some heat, so less heat will be provided to this diode. So if there is no limiting resistance, no resistance is there. Okay, if there is no current limiting resistance or no limiting resistance there, that means there will be a huge amount of current flowing through the diode. That means there will be huge amount of heat generated, and because of that heat, your device may burn out. Okay, so this is the problem. If there is no limiting resistance, the device may burn out in the breakdown region. But there are some devices or diode which are meant to be operated in breakdown region. So the name of that diode is Zener diode. So we use Zener diode in breakdown region only. How do we use it? What is Zener breakdown? What is Zener diode? Everything we will study now. So first I wanted to tell you avalanche breakdown, because many times they ask the difference between avalanche breakdown and Zener breakdown. This is a very famous interview question. What is the difference between Zener breakdown and avalanche breakdown? In PSUs, this may be asked. Okay, and even in Vivas also this is very famous question. What is the difference between avalanche breakdown and Zener breakdown? Okay, so that's why I first explained about the avalanche breakdown. Now we will study about the Zener diode. Okay, or Zener breakdown. First we will study about Zener breakdown, then we will study about Zener diode. So what is the symbol of Zener diode? The symbol is this. Okay, so now avalanche breakdown will not come in action. Okay, the role of avalanche breakdown is completed now. Now we will study about Zener breakdown. What happened in avalanche breakdown? In avalanche breakdown, electron had a more kinetic energy. So electrons were knocking off this silicon atom's bounded electron. These electrons were knocking out these bounded electrons. Okay, these electrons were doing this job. Now in case of Zener breakdown, what happens? In case of Zener breakdown, we used highly doped p-type semiconductor and highly doped n-type semiconductor. What do I mean by highly doped? That means there are more impurity. If there is more impurity, that means there will be more number of electrons and more number of electrons and more number of holes. Right? Highly doped means more number of charge carriers. Okay, look, there are so many electrons, 5 into 6, 30 holes I have made here, and 30 electrons I have made here. But in this case, I didn't make these much of holes, because this was lightly doped, this is highly doped. How do you show highly doped? By plus sign. Okay, p plus n plus. Okay, now in this kind of p-n junction diode, where p is highly doped and n is highly doped, the depletion width will be small. Why it will be small? Look, let's assume this was the electron here, this was the hole here. So these got diffused, like electron got diffused in the hole. Okay, this is fine. Now what happens? Now since there are a lot of plus minus, there are a lot of plus minus, that means there will be high electric field here, right? High internal electric field, because there are, look, the width is small, but in the width there are a lot of plus minus, no? Are you getting my point? The width is of one line only, but in this one line only there are a lot of plus minus. So because of that there is high electric field. So now if there is this high electric field here. So now if this electron wants to diffuse to this hole, this electric field will not let that happen, right? Now these electrons will try to go there, but it will give a force in this direction. So this electric field will not let that happen. Okay. So because of this high electric field, the diffusion width is small. Sorry, the depletion width is small, but E internal is very strong. Here, because of more doping, because of more doping, E internal is very strong. And also I am applying an external voltage as well. Now this electric field is so strong that this electric field itself is capable of knocking out these bounded electron. This electric field is so strong. In the avalanche breakdown, because of the electric field, electrons were moving, knocking out these bounded electrons. Are you getting my point? In avalanche breakdown, what was happening? Electric field was so strong, that's why electrons were getting more kinetic energy, and because of this more kinetic energy, they were knocking out these bounded electrons. So who were knocking out the bounded electrons? Electrons. And in case of Zener breakdown, electric field is knocking out the bounded electrons. Are you getting the difference? In avalanche breakdown, what was happening? Bounded electron of silicons were getting knocked out. But by whom? By high energy electrons. And in Zener breakdown as well, what is happening? The bounded electrons of silicon are getting knocked out. But by whom? By high electric field. Okay, so this electric field E internal plus E external knocks out the electrons from silicon atoms, knocks out bounded electrons from silicon atom. Okay, and thus they will create a lot of free electrons. This will be knocked out, or this may also be knocked out. So many of the electrons can be knocked out. This may be also knocked out. Okay, so this will create a electron and this will create a hole. This will create an electron and this will create a hole. This will create a hole and a electron. Okay, so in this way, electron and a hole. A hole is created, an electron is there. Hole is created and an electron is there. A hole is created and an electron is there. So in this way, there will be a lot of electrons, and because of that, there will be high current flowing. Okay, that means this breakdown region will be reached. So I will repeat it once again. There are two kinds of breakdown: avalanche breakdown and Zener breakdown. In avalanche breakdown, what is happening? Because of this high electric field, electrons are getting high kinetic energy, and these high kinetic energy electrons are knocking out the bounded electron of silicon, and because of that there are a lot of free electrons and a high current flows. Okay, in Zener breakdown, what happens? The internal field and the external field are so strong that the internal field and external field itself are knocking out the bounded electron of silicon, and thus there are a lot of free electrons and a high current flows. So I hope the concept is crystal clear to you. Okay, so in MCQs, I have seen in past question paper that these kind of questions are asked. So you should know what is happening. Zener diode, electric field, and avalanche breakdown, high energy electrons. Who is responsible in avalanche breakdown? High energy electron. Who is responsible in Zener breakdown? Electric field. Okay, so you should remember this. So that's it about the device physics. Okay, so generally this is a thing that your Zener breakdown occurs at a lower breakdown voltage than the avalanche breakdown, right? Like if we are using Zener diode, that means at lower voltage only we will get the breakdown voltage. Okay, generally the avalanche breakdown voltage is higher than the Zener breakdown voltage. Okay, this is for avalanche. This is for avalanche and this is for Zener. Okay, So mode of VB is greater than mode of VZ. That means you need to give a higher reverse bias in case of avalanche breakdown, and at a lower reverse bias you will get the Zener breakdown only. Okay, so this is our matter of interest. We will not go in avalanche breakdown. Okay, we will not go in avalanche breakdown. We will only talk about Zener breakdown only. Okay, so this is not a fact actually. There is a reason behind it, but this is not necessary to know. Okay, why does Zener breakdowns occur at a lower potential than the avalanche breakdown occurs at like why VB is greater than VZ. So there is a reason behind it, but you can remember it as a fact. Okay, we will study the reason in device physics, electronic devices. We will study. No one will ask you the reason. I'm pretty sure. Whatever they ask, what they ask is they will ask what is the region of avalanche breakdown and what is the region of Zener breakdown. Zener breakdown region is the electric field, and what is the region of avalanche breakdown? That are high energy free electrons. That's it. Okay, so this is the summary. Okay, now we will study the characteristics of Zener diode. So it is quite similar to that of a simple diode only. In forward bias, it is completely same, doesn't conduct, and after that it conducts exponentially. In Zener diode, in forward bias is the same as a diode only. Okay, and this is the sign of Zener diode. Okay, and in reverse bias, this is the condition when it is in reverse bias, and this is the condition when it is in breakdown region. So in diode we get a constant VZ after breakdown. Okay, so in Zener diode we get constant VZ after breakdown. Now you will say that, bro, there will be very high amount of current. So what is the use? The device may burn out. We will use limiting resistance. No, we will not let device to burn out. Now what is the thing? If your diode voltage is equals to Vz, now it can take any value of current. It can take this 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 value of current. It will give me a constant voltage nearly Vz, but it can take any value of current. When we studied about the piecewise not constant voltage drop model, what did I say? Now my diode voltage is fixed, that is V gamma. But now the current can take any voltage. Okay. Sorry, the current can take any value. So my voltage is fixed at V gamma, but my current can take any value now. Okay. And this is what is happening in this case. So this is the minimum value of IZ minimum. Okay. This is nearly equals to I saturation only. So this is the minimum value of diode current, sorry, Zener diode current in breakdown region, and this is the maximum value of Zener diode current in breakdown region. Okay, minimum value of Zener diode current in breakdown region. Okay, and this is the maximum. Yeah, what do I mean by IZ max? That is that this is the maximum current that can flow through the Zener diode. If your current is more than the IZ max, let's just assume a Zener diode has IZ max equals to 50 milliampere. Okay, and if you connect the diode in such a way that there is more than 50 milliampere current is flowing through the Zener diode, let's assume 51 milliampere current is flowing through the Zener diode, and at that value of current the device will burn out. Okay, are you getting my point? So this is the maximum current value that Zener diode can take. Okay, IZ max is the maximum current value, maximum current value that Zener diode can take. It's not lagging. I thought it's lagging. Yeah. So this is the maximum current value a Zener diode can take. That means after that voltage, sorry, after that current, the device will be burned out. Okay. So this is the concept. And yeah, look, it will try to give a near constant voltage. Okay, it will try to give a near constant voltage Vz. Okay, a near constant voltage, but the voltage may vary. Okay, a bit it may vary. So it will provide a low resistance. Okay, it will provide a very low resistance. Rz will be very low. It will try to give a nearly constant resistance. Sorry, it will try to give a nearly constant voltage, but there can be some small resistance. Like we have studied now these models for diode. In this you are getting complete constant voltage, that was 0.7 volt. But in this there was some resistance as well, right? It was not, it's lagging. It was not 0.7 volt constant, right? There was this R on resistance as well, which was also dropping of some voltage. So because of this dropping of some voltage, your Vd was greater than 0.7. It was V gamma plus ID RD, right? That was depending on ID and RD, right? So similar case is there in the diode one. Okay. Yeah. So now let's see those terms. Iz minimum. What is Iz minimum? When Zener is in breakdown, the minimum current the Zener diode will have. It will have means Zener diode will have. What is Iz max? When Zener diode is in breakdown, the maximum current it can have. Okay, if Iz is greater than Iz max, that means device will burn out. Okay, what is Rz? Rz is this. Rz. What is Rz? When Zener is in breakdown, the resistance it provides. It provides. It provides. When the Zener is in breakdown, the amount of resistance it provides, that is Rz. And what is Vz? That is the breakdown voltage of Zener diode. Okay, all clear to you? Characteristics of Zener diode. Okay, forward bias, everything is there. What is Iz minimum? Minimum value of Zener diode current in breakdown region. What is Iz max? Maximum current a Zener diode can have. And in Zener diode, we can get constant Vz voltage at breakdown, nearly constant. It will also provide some impedance as well or resistance as well, that is Rz. Okay, when Zener is in breakdown, it can provide some resistance as well. And what is Vz? That is the breakdown voltage of diode, Zener diode, and it will be mentioned in the question. Okay, yeah. So now there is a term called power rating of Zener diode. Okay, so it is written there many times in questions. It will be written what is power rating. So power rating is Vz into Iz max. Okay, so it is lagging. I have to restart. Okay, so what is the meaning of power rating? That means the maximum power a Zener, still lagging, a Zener diode can handle in breakdown region. Okay, so this is the definition of power rating. That means this is the maximum power it can take. Let's just assume this Vz is given, this Iz max is given. So what is the power rating? What is the, yeah, sometimes it is written that as what is the minimum power rating. Minimum power rating means they are talking about the power rating only. So you will note that you will not do Vz into Iz minimum. Okay, you will not do this because there is no meaning of this multiplication Vz into this. There is no meaning of this multiplication. Okay, the thing is this is the maximum current it can take. It can't take above this current. So Vz into Iz max. That's it. That's the maximum power it can have. Sometimes they also write what is the minimum power rating, or they sometimes write power rating only. So you can see sometimes minimum power rating. So at that time you will not do Vz into Iz minimum. You will just do Vz into Iz max only. That means it can't take above 5 into 40 milliampere. That means 5 into 40 milli, that means 200 milliwatt power. Okay, so this is the maximum power that can be dissipated across the Zener diode. If you dissipate more power, the device will burn out. Now the next question is given, a Zener diode has VZ equals to 5 volt, the power rating is 40 milliwatt, what is the maximum current it can take? Now on Zener diode the power rating is written, they have written that it is 40 milliwatt, and you also know the VZ, that means it will provide you a constant voltage of 5 volt. It is providing you a constant voltage of 5 volt, that means what is the maximum current it can have? This is the power rating that is written, power by voltage, that means 8 milliampere. So max to max Zener diode can take 8 milliampere current. So maximum 8 milliampere current should flow through Zener diode. That means for safer operation, you should only take 8 milliampere current through Zener diode. If the current is more than 8 milliampere, the device will burn out. So this is the meaning of power rating. Are you getting my point? Let's just revise the complete, not the complete, from here, from the characteristics. Characteristics in forward bias similar as the diode. In reverse bias as well, till breakdown region, the similar. After breakdown, it will provide me a nearly constant voltage. It will also provide me a resistance as well, that is RZ, and that is very low. So it will nearly provide me a constant voltage. Okay. There are two terms, IZ minimum and IZ maximum. So minimum value a diode will have. That means if the diode is in breakdown, this is the minimum value it should have. Okay. And what is IZ max? The maximum value it can take. The maximum value a diode can take. Let's just talk about this point more. What do I mean by IZ minimum? Let's just assume I am saying the IZ minimum for diode is 5 milliampere. Okay. And I am saying my diode is in breakdown region and the current I am getting is 3 milliampere. That means I am lying. My diode is not in breakdown region. If it is in breakdown region, minimum current that has to flow through the diode is 5 milliampere. That means if this is 5 milliampere, that means this is 3 milliampere. So the point is somewhere here. So this is not breakdown region. This is not VZ. This is much lesser than VZ. So that means this is the minimum current. That is the just as it goes into breakdown. Just as your Zener diode goes into breakdown, at that time it should drive 5 milliampere current. At least it can get more current, 5 milliampere, 6 milliampere, 7 milliampere. It can go get more current, but at least you need 5 milliampere current. So this is the meaning of IZ minimum. Okay. And IZ maximum current it can take. If you get more current than this, then your device will burn out. Okay. So this is the summary. And what is the meaning of power rating? Power rating means the maximum power it can dissipate. Now on the Zener diode, if it is written that your power rating is 40 milliwatt, okay, and your VZ is 5 volt, that means it will give you a 5 volt constant voltage. Now only 8 milliampere current should flow through it. If the current is more than 8 milliampere, that means the Zener diode will burn out. Okay. So this is the complete concept. Now we will see Zener diode in forward bias and in reverse bias, but before breakdown and then in breakdown. So how will we replace the model? Okay. So that we will see, and then we will see a few questions. Then we will see what is the use of Zener diode and everything. Okay. So let's just see Zener diode in forward bias. Okay. But I think I have to restart again. It's lagging, still lagging. Okay, I will restart. Yeah. So now it won't lag, hopefully. So let's see the different conditions. This is the diode. This is in forward diode. So I am giving positive to P and negative to N. This is P side, this is N side. Positive to P and negative to N. If it is on, it will simply behave as simple diode only. So there were three models. This was ideal. This was constant voltage drop. Forward bias means it is on, right? This is forward voltage drop and this is piecewise linear model. Okay, piecewise linear model, constant voltage drop and a ideal diode. That means it will be shorted, it will be replaced with a constant voltage and it will be replaced with a constant voltage and a resistance. Okay. Now the second model, the diode in the reverse bias but before breakdown. Okay. So the diode is in this region, till this region only. Okay. So this is the condition. So this is the VD we are applying. Actually VD we should write like this, because VD we are applying is negative, and this is the IDB we are getting. So VD you are applying is negative, that means you are giving higher bias to N side and lower bias to P side. Okay, so you are giving higher bias to N side, so that means it will be open circuited only. In any model it will always be open circuited. In sometimes it can be replaced with the high amount of resistance as well, if it is given in question. Okay, it's not given, sometimes they will tell you that in reverse bias your diode has a resistance of 100 mega ohm, so it is very high resistance. So it is rarely seen, but sometimes they can give this. Okay, so I hope you will be able to understand. Instead of open circuiting it, you will just replace the diode with this very high impedance. Okay, in 99% cases it will be open circuited only. Okay, so the ID current would be 0. Okay, and now the diode in breakdown region. Okay, so in breakdown region it will provide us a constant voltage. So tell me, how should I make the battery? It will provide me a constant voltage, that means I will have to make a battery, right? And the battery potential will be Vz. So how should I make, like this or like this? Think about it, take your time and tell me. The battery should be like this or this. Like this means the P side should be positive and N side should be, N side should be positive and P side should be negative. I am referring this one. I am referring this to this. That N side should be positive and P side should be negative. And for the inner one, N side should be negative and P side should be positive. So tell me what should happen. What should happen? P side should be positive or negative? So let's take an example and then see. Okay, which one is the correct? This one is the correct. P side is positive. N side should be positive and P side should be negative. Why is it so? Let's see that. Okay. Let's just assume this is my diode and I am saying I am having 0.7 voltage across it. How will I show it? First, let's just talk about the diode. How will I show the diode? P side and N side. Now we are having 0.7 voltage across it. So all fine. Now what is the scene? Now I am saying I am having a constant 6 volt voltage drop across it. P is at higher potential. P is at higher potential. Right? Now what will I say? So what will I do? I will make the battery. Now what is the potential of that battery? What is the potential of that battery? That is, what is the potential of that battery? That is minus 6 volt. Are you getting this point or not? My diode is, the voltage I am giving is this. That means I am applying plus 6 voltage here and 0 volt here. If I am saying this is my 6 volt, minus 6 volt, that means this is my VD, that is negative. That means I am applying 6 volt here and 0 volt here. That means I am basically applying 6 volt like this. So simply I can replace it with the battery of plus and minus, no? Or what I can do, or what I can see, from here you can see, if you are making this like this, minus plus and the potential is minus 6. So you can do plus minus and potential will be plus 6. So that at N side I am applying more positive potential. At N side I am applying more positive potential. So this N side will be made plus and P side will be made minus, because at N side we are having more potential. So whatever the side we are having more potential, that side will be placed with the positive, and the side where we are having lower potential, that side will be placed with the negative. That's it. That's the simple case. So if you want to place any diode with the equivalent battery, the side that is having more potential, that will be plus 6, that will be plus, and the side that is having lower potential, that will be minus. That's it. Okay. So this is how you can replace. Or what did I say? Sometimes it may provide you a low resistance as well. This low resistance RZ. Okay. Sometimes it may provide you a low resistance as well. And yeah, here the current would be IZ in the diode. It will be replaced with a single battery. At N side will be replaced with positive. If you can't understand it, just remember, N side will be replaced with the positive and P side will be replaced with the negative. Okay. So a battery and a resistance RZ. Okay. And the current flowing is IZ. And this total voltage would be Vz. So let's just call this potential as Vz dash. So Vz would be Vz dash plus Iz RZ. Okay, and here your Vz is Vz only, but here your Vz is Vz plus Vz dash and IzRz. So basically, in forward bias, you will treat that as a diode only. In reverse bias, you will treat that as a diode only and will open circuit it. And in breakdown region, it will give you a constant voltage with some current across it. Okay, you can find the value of this current by simple network analysis. Okay, and sometimes they may give you a value of Rz as well, that is it is providing a simple small resistance as well, that is Rz. So from there, the complete potential across the battery and across Rz, that would be your Vz. Just like in your piecewise linear model, what was your complete Vd? That was this V gamma plus IDRD. So this was your Vd, right? V gamma plus IDRD, right? So this is how you will replace them. Okay, now let's check let's solve this question. The Zener diode has a breakdown voltage of 5 volt. Iz minimum is 5 milliampere. Check if the Zener goes in breakdown region or not. Okay, Vz is 5 volt and Iz minimum is 5 milliampere. So let's take first circuit. Okay, you have to remember two things, that is Vz is equals to 5 volt and Iz minimum is 5 milliampere, that is given. Okay, now since I have 10 volt here, if I apply open circuit test, this will be open circuited. So at N side I am having 10 volt. At N side I am having 10 volt. So I would feel that the diode may get into breakdown region. Okay, let's just since this is the first question, what I will do, I am applying a short circuit test, open circuit test, sorry. Okay, so this is how I will solve it. I am applying an open circuit test. So what do I see? I see that I am having 10 volt voltage drop, 10 voltage drop from N to P, and my Vz is 5 volt. So it can go into breakdown region. Okay, so Zener can go into breakdown region. Go into breakdown region, right? So what I will do, the maximum potential it can have is 5 volt. What you are doing, you are applying a reverse bias voltage of 10 volt. You applied a reverse bias voltage of 10 volt, but this voltage you have applied in negative direction, so you can write minus 10. But what will happen, at this potential only the Zener will say this is my fixed voltage. Okay, now I can have any current, I can have any amount of current, but this is my fixed voltage, so I will be fixed at 5 only. But since at negative direction you are having more potential, that means it will be replaced with a battery of 5 volt. What should be the polarity of the battery? N side will be positive and P side will be negative. So 5 volt, and this is 500 ohm. Now you need to calculate Iz as well. So what is Iz? Iz is 5 by 500. 5 by 500, that means 10 milliampere, and this is greater than Iz minimum. So yeah, final conclusion is Zener goes into breakdown. Zener goes into breakdown. Okay, so this was the first circuit. Did you understand how did I solve it? First I will open circuit it. While doing the questions I will not actually open circuit it. I will just feel okay, 10 is there, so it may go into breakdown. 10 and the only breakdown voltage is only 5. So yeah, it is providing, we are providing high amount of reverse bias, so it will certainly go into breakdown region. So we will make a fixed voltage, that is 5 volt, and there also I calculated Iz as well. So Iz value I am getting, that is 10 milliampere, which is greater than Iz minimum. Okay, so that means this is the case that across Zener diode I am having only 5 volt. Okay, so now it can have any amount of current, right? It can have this 5 milliampere current, that is minimum. It can have this 10 milliampere current as well. So this is the current it is having. Okay, and this is the operating point of the Zener diode. This is the operating point of Zener diode. 5 volt and 10 milliampere. Got my point? So this is happening in the circuit. Okay, let's move on to the part B. What do you feel? You feel like that this will go into breakdown, right? Because Vz is 5 volt and Iz minimum is 5 milliampere. Since reverse bias voltage is 10 volt, then it feels like it may go into breakdown. It may go into breakdown, right? So it feels like, because you are applying 10 volt, that is very high. So if it feels like that it may go into breakdown, what you will do? You will replace that diode with a battery that is 5 volt. So yeah, it feels like it is in breakdown region, but tell me, what is the current here? Iz. Iz is 10 minus 5 by 5, 5 by 2000. That means 2.5 milliampere, which is lesser than Iz minimum, right? So is it going into breakdown? No, Zener does not go into breakdown. Okay, Zener does not go into breakdown. Are you getting my point? So what is happening here? This is the case. Okay, you thought so that, what did you think? You thought that you are here, but at 5 volt, you thought that you are here, but at 5 volt, this is the minimum current. That is, okay, I think I should make a large diagram. Okay, so you thought that you are here, 5 volt, minus 5 or whatever you can write, and let's just do like this. Okay, since this is providing zero impedance, so I can replace it with the straight line only. So you thought you are here, but at this point, the current is how much? At this point, the minimum current is 5 milliampere, that is given. But the current that you are getting is, what is the amount of current that you are getting? That is 2.5 milliampere only. So actually you are at this place. Okay, you are at this place. This is the point you are operating at. Are you getting my point? So any current below 5 milliampere will be considered as a zero only. Like, what I will do, I will replace this with open circuit only, because I don't know how it will look like in reverse bias. In reverse bias, it may provide some impedance based on this slope. Based on this slope, ID, this is VD and this is ID. So based on this slope, it may provide some impedance. But the actuality is, we make the graph like this, 0 and like this. So at 5 milliampere, the minimum at 5 volt, at 5 volt, the minimum current you expected was 5 milliampere, but the current you go to is 2.5 milliampere. That means you are somewhere here only. So your diode is not going into breakdown region. Okay. So the diode, okay, it is written. So Zener diode doesn't go into breakdown region. Are you getting my point? So it is in reverse bias only. So Zener is in reverse bias. So you may replace it with open circuit or the reverse bias resistance. I told you, no, it can be in some mega ohms or anything. So if it is given, you replace it with mega ohms resistance. Otherwise, you will open circuit it. Are you getting my point? The minimum current was 5 milliampere. If the Zener is in breakdown, the minimum current you have to have is 5 milliampere, but you are not getting that current. That means this is certainly not in breakdown region. Okay. Let's take the third example. So this was minus 10. What I can do, I can replace it something like this. This was minus 10. So what I will do, so Vz is 5 volt and Iz minimum is Vz is 5 volt, Iz minimum was how much? 5 milliampere. So tell me in which bias it is working. This is forward bias, right? If you apply a short circuit test, open circuit test, what do you see? Whatever the resistance it is having, that is 500 ohm. This is 10 volt. This is minus, this is plus. So at N side you are having minus, at P side you are having plus. So this is forward biased. So the answer is Zener is forward biased. Okay. Zener is forward biased. Let's see the final example. In this case, what do you think? Vz is only 5 volt and Iz minimum is 5 milliampere. So if Vz is only 5 volt, so 8 volt will be able to provide its 8 volt will be able to provide the voltage that it goes into breakdown. It may seem like that, right? It may seem like that, but if once you apply open circuit test, what will happen? If I am applying open circuit test, this is 8 volt here, 500 ohm here, 500 ohm here, right? This is the Zener. Across Zener, how much voltage is coming? Is it 8 volt? Across Zener, only 4 volt is coming. So here V Zener, we can say V Zener is 4 volt only. That is less than Vz. So Zener is in reverse bias, right? Although at N side you are getting positive value and at P side you are getting negative value. So it is in reverse bias, not in breakdown region. Is it in reverse bias? Not in breakdown. Okay. So these are the possible cases. So every time you have to check by applying open circuit test. You will see how much voltage is there. If it is less than the breakdown voltage, if the voltage across the diode is, if the voltage across the Zener diode is less than the breakdown voltage and the potential at P is lower than the potential at N, that means it is in reverse bias. If the potential at Zener diode is positive, that means P is at positive and N is at negative, that means it is in forward bias. And when the voltage across the Zener is greater than the breakdown voltage and it is in reverse bias, then you will replace it with the breakdown circuit. Are you getting my point? First thing you need to check is that it's forward bias or reverse bias. You first check it is reverse bias. Now you will check what is the voltage across the Zener. The voltage across the Zener is greater than Zener breakdown voltage. That means it will go into breakdown region. Here it was less, so it doesn't go into breakdown region. Here it was forward biased only, so forget about it. It was forward biased only. In this case, yeah, the voltage was fine, but the current was less. Here the current was 2.5 milliampere only. That was less than the minimum current, minimum Zener current. So Zener doesn't go into breakdown region. And in the first case, what did you see? It was Vz was also fine because of 10 volt, it was going into breakdown region, and also the current was also fine. Okay, current was also greater than the Iz minimum, so it goes into the breakdown region. Did you understand the complete concept? Just revise it once again. Everything will be crystal clear to you. Okay. Now let's see where the Zener diode are used. Okay, so Zener diode are used as a voltage regulator. Now the question is, what do you mean by voltage regulation? Okay, so what do I mean by voltage regulation? Let's just assume I have a voltage that is varying from This is my input voltage V in, that is varying from any, with respect to time or anything you can say, that is varying from some 5 volt to somewhat like this to some 10 volt. Okay, I should make it a better waveform. Okay, somewhat like this to 10 volt. So from 5 to 10 volt it is varying, but you need a constant voltage at output. What do you need? A constant voltage. So for that you will use a Zener diode, because Zener diode gives you a constant voltage, right? So this is what I need at a output, a constant voltage. It can be any value, right? This is a constant voltage you need. I'm calling that voltage as Vz. So this is what you need. So here your Zener diode can be used. Okay. So there are basically two conditions. So voltage regulation is required in these conditions. In what condition voltage regulation is? Did you understand the concept of voltage regulation? Having a constant output at the, having a constant voltage output, having a constant or regulated voltage output. Look, having clear VZ is very difficult, but you can have somewhat like this, right? You can't make a ideal battery. There will be some resistance as well. So in case of Zener diode, you will have a VZ and a small RZ as well. So there will be a little slope also. Okay. Not with respect to time. I should just keep this as it is. What should I write here? Time is not something I should write. Time also can be there. X-axis can be anything. It can be current as well. It can be time as well. It can be anything. You just need a constant voltage at output. This is what you need. Okay. So it can be anything. So let's just assume, what do I mean by, like, where do I actually need voltage regulation? Look, line variation, that means your supply is varying. Your supply is varying from 5 volt to 10 volt. When your supply was 5 volt, when V in was 5 volt, what was your output? Output was 3 by 5 into 5. That means 3 volt. So when your input was 10 volt, what was your output? Output was 6 volt. So basically your output is varying from 3 volt to 6 volt, and you do not want that, right? Your output is varying from 6 volt to 3 volt and you do not want that. Now my input is fixed, still my output can vary. When my load is varying, so that is load variation. If my load is RL is 3 ohm, so my output will be 3 volt. And when my RL is 8 ohm, my output is 8 by 10 into 5. 8 by 10 into 5, 4 volt, right? So my output is varying from 3 volt to 4 volt. Because of what? Because of the load. Okay. In this case, your input was varying, your supply was varying. Because of that, your output was varying. In this case, your supply is fixed, but your load is varying. So two things can vary: supply and load. Both also can vary. If both varies, your output will have different range. So you don't want this. You want a constant output voltage. You want a constant output voltage. For that, you will use Zener diode voltage. Okay, so for that you will use Zener diode. Here your output is varying, but you want a regulated output voltage. That means a fixed output voltage. So that's why you will use a Zener diode. Okay. Now we will take cases. In first case, your supply is varying. That means this case, your supply is varying. Okay. So understand this very, very clearly, very, very neatly. Okay. Just give your full attention here. Okay. So tell me, what do I call it? I call this current as IS. I call this current as IZ, and I call this current as IL, load current. load current, Zener diode current, and source current, I will say. Okay. Now my supply is varying. This is fixed, right? RL is fixed. Okay. Now I am considering that Zener goes in breakdown region. So if Zener goes in breakdown region, what will be this potential? This potential will be fixed as VZ only, because this will be replaced with the battery of like this. So this VZ potential will be fixed. Now VZ is fixed, RL is fixed. That means IL equals to VZ by RL. RL is not varying. RL is fixed. VZ is also fixed. That means this is fixed. Right? Your IL is fixed. Now, what is your IS? IS is IZ plus IL. Look, don't focus much on the equations. Okay, this is the second equation I can write, and this is the first equation I can write. And there can be one more expression of IS, that is VS minus VZ by RS. VS minus VZ by RS. This VZ is fixed, RS is fixed, only this is varying. So if VS is minimum, okay, if VS is minimum, that means your IS will be minimum, and IL is fixed. If IS is minimum, that means IZ will be minimum. Are you getting my point or not? Look, this is very important concept, and 90% of student fails to understand this concept. What I will do, first in the question, what I will see that my load is not varying, load is fixed. Okay, that means my load current will be fixed as well. Because of the Zener voltage, my load current will also be fixed. My load current is fixed. Now my Zener diode can have any amount of current, right? From IZ minimum to IZ max. Okay, if IZ minimum is not given, many times you consider it to 0. Okay, so from 0 to IZ max, it can have any amount of current. Now, how much current will be flowing in the Zener, that will be dependent on the supply. Okay, so when RL is fixed, and if the current in the Zener is minimum, that means the supply is minimum. Are you able to take this point? Load is fixed. If the current in the Zener is minimum, that means the supply is minimum. Because if the supply is minimum, that means it will provide the minimum current, that minimum IS current, and if the IS is minimum, that means IZ will be minimum. Are you getting my point or not? This is the most important point of this chapter. Only 2 points are there. If you know these 2 points, you will be able to solve any problem of Zener diode. This is the first point. That is, if Zener is having minimum current, that means supply is also at minimum, and if Zener is having maximum current, that means your supply is also at maximum. So kind of what you can say, Zener current is proportional to supply voltage. Kind of you can say. If supply is less, that means Zener current will also be less. So this is the most important point. Okay, so again and again I will use this. What I will say, this and this, these two are brother. The IZ and VS are brother. If IZ is minimum, that means VS is minimum. If IZ is maximum, that means VS is the maximum. This and this are brother. Okay, they are brothers. Okay, they are brothers. If IZ is minimum, that means VS is minimum. Okay, so this is the thing you need to remember. Okay, very important point. Many times students get confused, because now what will happen, your load will vary this time. Your supply is fixed, VS is fixed. Instead of Vx, I should write a It's like a battery, not varying. This is fixed now. Vs is fixed now, but your load is varying. This current is IL, this current is IZ, this current is IS. Okay. Now tell me what is IS. IS is Vs, considering Zener in breakdown. Okay, considering Zener in breakdown. If it is not in breakdown, it will simply be a diode circuit problem only. If it is on, this will be a battery or resistance, and if it is off, this will be open circuit. So if it is not in breakdown, it will be a simple diode circuit problem that we have already seen. So that's why I am considering Zener to be in breakdown. Considering Zener in breakdown. Okay. Considering Zener in breakdown. So if I am considering Zener in breakdown, so that means what will be my IS? IS will be Vs minus Vz by Rs. Isn't it is fixed? Isn't it fixed? Vs is fixed, Vz is fixed, Rs is fixed. Everything is fixed here. So my IS current is fixed. Now let's talk about IL. What is my IL? IL is, this is in breakdown, so Vz by RL. Right? This is the second equation. What is my third equation? That is 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 equals to IZ plus IL. Right? This is the third equation. When RL is the maximum, when this load is maximum, that means this current will be minimum. IL will be minimum. Since this is fixed, that means this current has to be maximum. Are you getting my point or not? My load is maximum. That means my load current is minimum. If my load current is minimum and the current that is coming from here, that is constant, so that means this current has to be maximum. One current is minimum, so other current has to be maximum, right? If my load is maximum, if my load is minimum, that means my IL will be maximum. If this IL is maximum, that means IZ has to be minimum. So that means these two currents are enemies. If IL is maximum, that means IZ will be minimum. If IZ is minimum, that means IL is maximum. Are you getting my point? So I will write, I'll just write this point. If, what do I need to write? If RL is max, that means IL would be minimum, and that means IZ has to be maximum. If RL is minimum, that means IL has to be maximum, that means IZ will be minimum. This is the case. Okay, this is not, you will remember, I will write it in the theory like this. That means if load current is minimum, Zener current would be maximum. And if the load current is maximum, the Zener current would be minimum. Okay, so kind of inverse proportion. Okay, I will write analogy here because someone will say he is teaching wrong. Okay, this is just an analogy. What do I mean by analogy? kind of relation like that, inverse proportion. If one is minimum, one is maximum. Like, you can't derive any formula, but this is just an analogy, right? If Iz is minimum, that means IL will be maximum. If IL will be minimum, that means Iz will be maximum. This is also an analogy. Okay, this is also an analogy. Otherwise, people will say I teach wrong. Okay, this is also an analogy. Okay, so these are analogies. So let's just solve. Now you can get it out. What if both are varying? Even the supply is varying, even the load is varying. So there will be a one question that will clear it out. Okay, I am not taking as a case. Okay, I am not taking it as a case. Okay, we will see that condition when load is also varying and Vs is also varying. We will see that condition by a question. So all your doubt will be cleared in that question. Okay, now let's just solve a problem. In this case, what is happening? Neither the supply is varying nor the resistance is varying. Although I have given a different voltages, so we can take that the resistance is varying. So basically in this you need to find the current through the Zener diode. For first case V0 is 3.5 volt. For the second case is V0 is 3 volt. Okay, Vz is given, that is 3.3 volt, and Rz is 0.1 kilo ohm. Okay, let's take first case when your V0 is 3.5 volt. Okay, 10 volt battery we are having here. 2.2 kilo ohm. Now tell me one thing. Now they are saying that here we are having 3.5 volt. Across Zener, how much voltage do you need? Only 3.3 volt. That means it will certainly be in breakdown region, right? 3.5 volt. At N you are having positive, at P you are having negative. So in negative direction you are having voltage, that is 3.5 volt, and Zener breakdown is 3.3 volt. That means certainly it will go into breakdown region. Certainly it will go into breakdown region. So it will be replaced with the battery and a resistance. Okay, and this is R1. This value of R1 here is 3.5 volt. Now this is 3.3 volt battery, 3.34 volt battery, and R1 value is 0.1 kilo ohm. So this is 3.3 volt battery, and here you are having 3.5 volt. That means rest of the 0.2 volt you will be having here. Across 0.1 kilo ohm you will be having 0.2 volt, because across the whole Zener diode you are having 3.5 volt. 3.3 is eaten by the battery, so rest of the 0.2 will be across the resistance. So what will be your Iz? Your Iz will simply be voltage by resistance. That means it will be 2 milliampere. Are you getting my point? This is the first case. Now in the second case, what do you think? V0 is equals to 3 volt. Will the Zener go into breakdown? V0 is equals to 3 volt, so 3 volt will be coming here. How much voltage do you need? You at least need 3.3 volt. So it won't go into breakdown, right? So it will not go into breakdown region. Okay, so in the second case, Zener doesn't. Okay, I can use the next page as well. So for second case, so what will be the Iz value? That will be 0 only. So let's just write it clearly, because some people will be reading notes only. So for them I am writing it clearly. 10 volt 2.2 kilo ohm. Okay, and here you are having 3 volt only. So this is your Zener. This 3 volt goes across the Zener. So the Zener is in reverse bias, because at P potential you are having more positive voltage, and sorry, at N you are having more positive voltage, and at P you are having less positive voltage. At P you are having negative voltage, at N you are having positive voltage. So Zener is in reverse bias, not in breakdown, right? So this will simply be open circuited, right? So Zener will simply be open circuited, and this is your Iz. That means your IZ would be 0 ampere. Okay, so IZ would be 0 ampere because the Zener is in reverse bias. Now this is the condition. This is the circuit given to you. The Zener diode in the circuit shown in the figure has a knee current. Knee current is the minimum current. Okay, sometimes they use this term knee current. Knee current is the minimum current. Minimum current. Okay, that is IZ minimum that is given is IZ minimum is 5 milliampere. Okay, VZ would have also be given. So the second condition that is given is a maximum allowed power dissipation is 300 milliwatt. What are the minimum and maximum load current that can be drawn safely from the circuit, keeping the output voltage constant at 6 volt? You need a 6 volt constant output voltage here. That means your VZ has to be 6 volt, right? And what is given? Your maximum power dissipated allowed of Zener allow maximum allowed power dissipated that is 300 milliwatt. That means your VZ that is 6 into IZ max that is the maximum current it can draw. That would be 300 milli. That means your IZ max would be 50 milliampere, right? IZ max will be 50 milliampere, IZ minimum is 5 milliampere. Okay, IZ minimum is 5 milliampere. Now tell me if this is fixed at 6, that means 9 minus 6 by 50. That means how much current is coming from here? IS. How much is IS current? IS current is 9 minus 6, 3 by 50. 6 by 100. That means 60 milliampere current is coming. So from here we are having 60 milliampere current. Now 60 milliampere current will be divided between 2. Here your load is not fixed. They are asking what is the minimum and maximum load current that can be drawn safely. So IS is 60 milliampere. First condition is that if IZ is minimum, if IZ is minimum, that means what will happen? IL will be maximum. IL will be maximum, right? So from here you can say that IS is equals to IZ plus IL, right? So this 60 milliampere is fixed. 60 milliampere is fixed. If IZ is minimum, that means IL will be maximum, right? So 60 milliampere, IZ minimum is 5 milliampere. So IL max is 55 milliampere. So this is the first answer. Okay, I can use a different box or that is fine. And what about the other case? IS is fixed, that is 60 milliampere. If IZ is maximum, that means your IL will be minimum. What is your IZ maximum? Maximum current it can take is 50 milliampere. So your IL minimum would be 60 minus 50, that means 10 milliampere. So basically the range of load current is 10 to 55 milliampere. Are you getting my point? What did I do? First I found out what is the minimum and maximum current in the Zener diode. Minimum current in the Zener diode is 5 milliampere. What is the maximum current in the Zener diode? That is 50 milliampere. So from 5 to 50 you can have the current in Zener diode. Now there is a constant current 60 milliampere is coming from this side. So if my Zener is having 5 milliampere current, that means my load will have 55 milliampere current, right? If my Zener is having 50 milliampere current, that means my load will have 10 milliampere current. That's it. Very easy question, right? These kind of questions, if you are well aware of the concept, it won't take you more than 1 minute to solve this problem. You will just read it. Okay, you will see maximum minimum current. That means here also I can find maximum minimum current. That's it. Here load is not varying. Here your voltage supply is not varying. So this is the case of load variation, right? This is the case of load variation. We will see the case of supply variation as well, but later on. Now in this case IZ minimum is given, VZ is given. Okay, Iz minimum and Vz is given. The value of R required for satisfactory voltage regulation of the circuit is, okay. Here both supply is also fixed and final voltage is also fixed. Okay. Now for satisfactory voltage regulation of the circuit, that means this has to go into breakdown. The Zener has to go into breakdown. That means then only there will be voltage regulation. No, if there is voltage regulation, that means Zener has to go into breakdown. Has to go into breakdown, right? So this is 20 volt. This is resistance R. Zener has to go into breakdown. This is the resistance R. And this is 100. So this will be a 10 volt battery, right? So 10 volt battery is here. So 10 by 100, that means 100 milliampere current is there, right? So here we are having 100 milliampere current, because this 10 volt will be here as well. 10 volt here and 100 milliampere current. Now the minimum current that has to go through Zener is 25 milliampere. Okay, to make this question interesting, what I will do, I will give you Iz max as well. Okay, your Iz max is 50 milliampere. Now people will think, which should we use, minimum current or maximum current? So tell me, what should you use, maximum current or maximum current or minimum current? Here it is written satisfactory voltage regulation. That means the minimum required condition for voltage regulation. If it was written safe voltage regulation, that means the current cannot go above 50 milliampere. Safe means the device should not burn out. Satisfactory means the minimum condition. That means the minimum condition. And what is the minimum condition? That it should have a minimum current of 25 milliampere here. That means from here we should have 125 milliampere. So basically 20 minus 10 by R is equals to 125 milliampere. So from here you can get the value of R. So that will be 80 ohm, I guess. And 1 by 8 is, yeah, 80 ohm. So R value you get is 80 ohm. Okay, you understood what is the point? Why didn't we take Iz max? Because they are asking what is the satisfactory voltage regulation. That means the minimum condition where voltage regulation will occur. So the minimum condition where voltage regulation will occur is that minimum current. So that means it should have a 25 milliampere current. And here we are already having, because of 10 voltage, here we are having 100 milliampere current. So 25 plus 100, that means here we are having 125 milliampere current. So 20 minus 10 by R is equal to 125 milli. That means the value of R required is 80 ohm. Okay, let's move on to the next problem. Find the voltage range of V in for the Zener to remain in on and safe. On and safe. Safe means maximum condition. On and safe. So Vz is given, Iz max is given. Even Iz minimum I will give, so that you guys get confused. Which one should you use? So which one should you use? The Iz max one, right? Because safe they have written. Right? So what will happen? On and safe, that means the Zener will go into breakdown. So if it goes into breakdown, it will give a constant voltage drop of 20 volt. Constant voltage drop of 20 volt. And since they have written safe, that means it will have 50 milliampere current. And here we are having 2 kilo ohm resistance. This is my input. So 20 by 2k, 20 by 2k, 20 by 2 kilo ohm, that means 10 milliampere. So basically we are having 10 milliampere current here. This 20 volt will go across 2 kilo ohm, that means 20 by 2k, that means 10 milliampere current here. So that means we are having 60 milliampere current here. Okay, actually they are asking the range of input voltage. Okay, they are asking the range of input voltage. That means for both minimum and maximum condition you need to find on and safe state. What does on means? The very time it gets turned on, so that will be the minimum condition, no? So they are asking the range, that means they are asking both minimum and maximum. Okay, this shows the minimum condition on state just as the time it turns on. Okay, so here we are taking if Iz is maximum, that means your Vs will be maximum, right? Or Vin will be maximum. Vin is going to be maximum. So you will get the maximum voltage now. So Vin minus 20 by 250 is equals to 60 milli. That means it will be 1 by 4 kilo. So 15. So Vin will be Vin max. This is your Vin max. That will be 35 volt. Right? Vin max will be 35 volt. Okay. Now I can copy the same diagram. But now my current in the Zener will be the minimum current. Okay. In my current in my Zener would be the minimum current. Okay. In this question, Iz minimum was not mentioned. When Iz minimum was not mentioned, you should have taken the current to be 0 ampere. Okay. Iz minimum, let's just remove this current. Okay. Iz minimum is not mentioned. So here I will take 0 ampere current. Okay. Iz minimum not mentioned. Okay. If Iz minimum is not mentioned, I will take Iz minimum equals to 0 ampere. Okay. So Iz minimum is 0 ampere. So if Iz is minimum, that means your Vin will be minimum. Your Vin minimum minus 20 by 250 is equals to not 60. If here I am having 10 milliampere current, this 10 milliampere current is fixed because 20 volt will be going there. So Vz is fixed, RL is fixed. So 10 milliampere current is fixed. 10 milliampere current is there. So here we will be having 10 milliampere current. So Vin minus 20 by 250 is equals to 10 milliampere current. 10 milliampere. So 10 into 1 by 4 kilo it would be. So 2.5. So V in minimum is 22.5 volt. Okay. So V in minimum is 22.5 volt. Got my point? Let's move on to this question. This is a very, very good question. I hope this is the last question. So this was the case of supply variation. Okay. Supply variation. This was the case of not load variation. This was supply variation. Right. Here your input is varying. Now this is the case of both load and supply are varying. So Vz is given, Iz minimum is given, Iz maximum is given. You have to find the maximum and minimum current drawn by the load. Where is the load? This is the load. Okay, this is the load. The value of load is not given, RL is not given. So you have to find the maximum and minimum current drawn by the load, and input voltage is ranging from 20 volt to 30 volt. So this is ranging from 20 volt to 30 volt. Okay, and this Vz is 5.8 volt. Okay, so now tell me, I need to find maximum current drawn by the load. Okay, so maximum current drawn by the load current I will say IL, this is my Iz, and this is my Is. Now I will write down the things. This is the case of load variation plus supply variation. Okay, we don't need to be tensed about it. We just remember two things. If load current is maximum, that means my Zener current will be minimum. If load current is maximum, that means my Zener current will be minimum. If my Zener current is minimum, that means my supply is minimum. I will just write down this thing. If load current minimum, that means my Zener current is maximum. Current is maximum. That means my supply voltage maximum. And if my load current is maximum, that means my Zener current is minimum. That means my supply voltage minimum. If these two lines you remember, there will not be a single problem which you can't solve for Zener diode. Most important line. Now, what happens in this question if this comes in exam? Okay, what people think, that I will tell you. They are saying that find the maximum load current. Okay, find the maximum load current. So what they will do? They will first say that you have to find maximum load current. That means here the current should be minimum. So here they will say that this current should be minimum and this current should be 0.5 milliampere. Okay. So they will take this current to be 0.5 milliampere. Now they will say that since I need maximum current, in the load, so I will take maximum voltage here. I will take 30 volt here. But if you are taking the supply to be 30 volt, there is no chance that this IZ will be minimum. Are you getting my point? What student will think? Student will think that I need maximum load current, so I will take supply to be maximum. But if you are taking supply to be maximum, at that point the IZ will be also maximum. Why so? Because this is the case, no? If the supply is maximum, that means the current will also be maximum. Because here if the supply is maximum, your IS will be maximum. If supply is maximum, IS will be maximum. This will also have the more current. Okay, so supply is the brother of Zener current. Always remember it. Supply is the brother of Zener current. Okay, so I will first solve what will be the mistake by the student. Okay, so first is the maximum load current. Okay, maximum load current you need. So what the student will do, this is the resistance, this they will make the battery is of 5.8 volt, 5.8 volt, better make it like this, and there is this load is there. Okay, this load is there. Here you need maximum current. Okay, here you need maximum current, so here you will have minimum current. For max current, I will take supply to be max. That means I will take supply to be 30 volt, and here I am going wrong. Okay, so what will be my answer? Let me check. So what was my minimum current? Minimum current was 0.5 milliampere. 0.5 milliampere, right? Yeah, 0.5 milliampere. I will take my supply to be maximum. That means I will take here 30 volt, and this is 1 kilo. So this is 30, this is 5.8. That means here I will have 24.2, right? 24.2, 35.8, yeah. So here I will have 24.2 milliampere current. 24.2 milliampere current. And if I am having 24.2 milliampere current, my IL max would be 24.2 minus 0.8, that would be 23.7 milliampere. And this is the complete wrong analysis. Okay, this is the complete wrong analysis. Okay, why is it wrong? Why is it wrong? Because when your supply is maximum, the Zener current will surely be maximum. Then Zener current will certainly be maximum. And if Zener current is maximum, the load current has to be minimum. If Zener current is maximum, the load current would be minimum. That means in this case at 30 volt you will not have 0.5 milliampere current, you will have 20 milliampere current. So in 30 volt you will have 20 milliampere current here. In this case, although I will write 0.5 milliampere current here because this is the wrong analysis that I am saying, which is the wrong, this is the complete wrong analysis that I am saying. But here actually you will have 20 milliampere current because this is the maximum Zener diode current. This is the maximum Zener. So actually you will have 20 milliampere current. From here 24.2 milliampere current is coming, 20 milliampere current is going that way. At that time your IL current would be 4.2 milliampere. So that is the minimum current the load will have. So simply you need to remember this thing. This is the only thing you need to remember. For minimum load current, or whenever they ask minimum source voltage, if they are asking minimum source voltage or minimum input voltage, that means you need minimum Zener current, and minimum Zener current means maximum load current. Only this much of scenario you need to remember, and every single problem will be solved. Otherwise you will mess up the problem. Okay, I have seen a lot of students messing up Zener diode problem because they don't read these two lines. Only these two lines will help you solve all the problem. That is minimum load current, maximum Zener current, and maximum Zener current means maximum supply voltage. That's it. Okay. So here we will solve it correctly. So first is the maximum load current. That means minimum Zener current, and that means minimum supply. So what is my minimum supply? That is 20 volt. Okay. So 20 volt here. Here I am having a limiting resistance, whatever that is. This will be replaced with the 5.8 volt battery. 5.8 volt battery. 1 kilo ohm resistance is there. You need the maximum current in load, right? So 20 volt was there, and here 5.8 volt is there. So here the current is 14.2 milliampere current is there, and the current in Zener is minimum, that is 0.5 milliampere. That means this is your IL max, right? So 14.2 is coming from here, 0.5 is going there. So that means your IL max would be 14.2 minus 0.5. That means 13.7 milliampere. That's it. And for the second case, minimum load current. That means maximum Zener current. Okay, minimum load current, that means maximum Zener current, and maximum Zener current means maximum supply. So you will give the maximum supply. That means you will give 30 volt here. The Zener will certainly go into breakdown. The Zener will go into breakdown. 30 volt here. You have a limiting resistance of 1 kilo ohm. Limiting resistance of 1 kilo ohm. Okay, so you are having 30 volt here, and you are having minimum load current, that means maximum current here. What is the IZ maximum? That is 20 milliampere. Okay, so you are having 20 milliampere current here. That means 30 minus 5.8, that means 24.2 milliampere current is coming this way. 24.2 milliampere. This is your IL minimum. So your IL minimum would be 24.2 minus 20, that means 4.2 milliampere. That's it. Well and good. So these are your two answers. Okay. So this is the complete concept, and this was the most important question that clears your complete concept. Only one line will be more than enough. You need the maximum load current, that means you need minimum supply current, minimum Zener current. If you need minimum Zener current, that means you need minimum supply. Okay, if you need minimum load current, that means you need maximum Zener current. If you need maximum Zener current, that means you need maximum voltage supply. So that's it. And this is the complete concept of Zener diode. I hope you liked the lecture. In every lecture, I just hope you are understanding something new for sure. Even if you have studied the topic previously, I hope you have studied something new here. Okay, and if you have studied something new, if you have learned something new, please do comment. Okay, please do comment, and please do share this channel with your friends. Okay, so in every topic we will go in such depth that no question can be wrong. Now this question is asked in the exam. Okay, in 2 marks, everyone will solve the question very quickly, and everyone will solve like this, because here you are getting 23.7 milliampere current, right? And here you are getting maximum current as 13.7. So everyone will think, oh, this is the more current, that means this should be the answer. But what is the catch here? The catch is that if you are having maximum current, that you can't apply maximum voltage. You have to apply minimum voltage. So if they are applying minimum voltage, then only you will have the maximum current. Okay, if you are applying the maximum voltage, that means Zener will also drive maximum current. Zener will also drive maximum current. So in this case, actually Zener will drive. In this case, if 30 is there, that means the Zener will drive 20 milliampere current. So in this case, the current would be 4.2 milliampere, not 23.7 milliampere. That's why this answer is wrong. So I assume many of the students would have solved like this, but I hope you won't do the mistake again. Okay, so if you have liked the lecture, please do share it with your friends. Okay, so that it reaches to every possible people. Okay, thank you.